Welcome back. This is tutorial 5, Trends and Cycles for Applied Econometrics for Macroeconomics and Finance. Today, we'll be talking about the unit root and about a test to identify if we have, or to be more specific, if we can't reject not having the unit root in our term series. And for this test will be the augmented Dick-Fuller. But first, let's do some admin. Your quiz is due this Friday, so please pay attention and make sure you submit it before 4. And you see here they're very specific at 3:59 p.m. Probably if you're playing a risk game, 59 seconds, but not 4. As soon as it clocks to 4, it probably stops you from submitting. So don't forget to submit in case you haven't yet. Okay. What else do I have? Just calling your attention, this week I released the new version, and 2 days later, I think this morning, our studio released the new version too. You probably will get a few warnings when you're running the code, when you're loading libraries, because the new versions of the libraries are being recompiled for the newest R. But don't worry, you don't need to rush and install the newer version or RStudio right now. Do it at your own time, I think, as we do with apps in our cell phone or our computer. It's a good idea to have it updated so you have the newest and corrected versions, but I don't think it will get in the way of completing this tutorial, so you should be fine. But these are the newest versions of both. One came out on Monday, one came out today. Okay, so let's go. Tutorial 5, Trends and Cycles. At the end of this tutorial, you should be able to construct an adequate set of ADF, augmented Dick-Fuller, specifications for unit root testing, and then carry out ADF tests for the unit root and interpret the results. Then construct an adequate set of general RIMA PDQ models. All right, so let's start slowly. The first thing to do, could you please download the usdata.csv from our learning resources, then week 5, then you go down to tutorial 5 and download these guys. If you want to download the PDF, I think it's always a good idea to have it there, but it's not necessary. You would only need the CSV. Next, after you do that, I'll ask you to access this code, this link for code share. So tutorial 5 is already there, and I would like to copy it, but I don't know if it's allowing me. No, so I will do something else. I'll just copy for the people that are online right now. I will share on chat. And if by any chance it doesn't work, please let me know. Let me see. Yeah, it did. For the other people, I think something that is hasn't been really clear is that the answers I'm sharing with you in this code share things are exactly the same answers that we have on the PDF solution. And the PDF solution is the official answer to it. All right, so like if, for example, this code share, I don't think it stays there for very long. It stays for a few days only, and I'm only doing that because the solutions are not available yet. So I'm sharing with people watching the tutorial live so they can follow the code. But as soon as the other solution is available, you can use that one. The difference, the only difference we have in between both would be just some comments that I add to the code, so it helps me going through the tutorial. But other than that, you're not missing anything if you get the PDF from the official the solution from the official PDF, kind of, or the other way around. Okay, just to make it clear, because we got a few students asking like, how can I access? I can't access anymore, etc. But the PDF is the one to go for. That's it. All right. So 3350, please create a new script, paste the script in there, and save in the same folder that you saved the usdata.csv. Okay. Now, let's go. Tiny bit of theory. And in this slide, we might be coming back to this slide a couple of times while we are doing all our explaining the code. Okay. This is ADF. We want to do an augmented Dick-Fuller test to check if we have a unit root in our time series. And what is the problem with a unit root? It would be that A1 multiplying this guy here, A1 multiplying YT minus 1 is equals to 1 if there is just one leg, or if all these guys combined adds up to 1. And this is a problem because instead for our time series, instead of going down with time, the effect of the previous legs, they will just be continuous all over. So it tends to explode in the end, the value. So as you keep on adding legs and going to the next and the next and the next, it should grow to the infinite. Kind of, so this is what's going on. And during the ADF, we will split in 3 cases. One where there is no drift, and the drift is this little constant we have here, and one with drift but no trend. The trend is this guy here, this delta t. And the third case where we have both, we would have a drift or a constant, and we will have a delta t, a trend. And if you look at this whole thing here, I would like to expand a little bit on what it looks like. I want to draw what color? Blue is all right. No, I want a different color. Green. Look at this guy. If I told you YT is equals to, remember our simple linear regression, a B0 plus B1 X plus an error. Try to think, this is a little bit of a regression. Try to think this is, the T is actually this X. So I will take the X and now I will draw an T, a T here. And the epsilon is then our ARMA model. So epsilon is this whole thing in here. And if you remember from our ordinary list squares, etc., we want this guy here to have a mean expected value equals to 0. And we want it to be homoscedastic or have a constant variance, right? So if we remind you a little bit of what we were talking about, our ARMA model, and it will be really interesting. If you watch the pre-recorded tutorials, you see Dominic saying that in the past, that's exactly what they did. First, they ran a regression. Then the ARMA models were actually how they were analyzing the error or the residuals. Oh, can I text? So also residuals. So this is how these were the initial ways of dealing with ARMA. So looks like a little regression, but we will be testing more things around that. But just to give a little bit of background, you will see in the pre-recorded videos and in the lecture this week, week 5, Eric expanded and explained a lot more about it. I would strongly suggest you to watch it too, if you haven't yet. Okay. All right, let me clean it all. So no drift, no trend, looks like our standard ARMA model. But then we're moving to this delta with a gamma and the other things, okay? It's a delta, is the change or the difference. With a drift, it's just the A0 there. And with drift and trend will be the A0 plus this little delta t, which you should think like the slope coefficient and the independent variable or exogenous variable. In our case will be time. Okay, let's go. So also you will find this slide here in lecture 5, slide 70. First, the file usdata.csv contains 209 observations on both GDP and federal funds rate, which we'll call in interest from here on. And first, for YT or for GDP, plot the observed time series and comment on potential trends. Let's go. Massive code, and then I added some comments, and now it looks like it has 470 lines. I hope it doesn't scare you too much. A lot of this is comments. First, we started with cleaning, house cleaning. So we're cleaning the environment, then we're cleaning any plots if we had any, and now we're cleaning the console. Next, that standard line of code that I add, it's just setting our working directory to be the same at where you saved your script. So it's the same as doing session, set working directory to source file location. Exactly the same thing, okay? You probably need this library installed, RStudio API, but we've done it before. So let's go. We will run these 3 libraries that we used before: forecast for the ARIM and a few other functions, Dipler, and Zoo. Zoo is going to be the one we use for dealing with our with dates and years. And Dipler, I can't remember, to be honest, why we use which function it is, but we will find out. And then this is new. We're going to add the alternative time series analysis, ATSA library. Probably I wouldn't expect you to have it installed, so I left this line there. So please run this one to install, and then you run library ATSA to load it. After you've installed, I would suggest you just to comment this line, because then you don't need it anymore, right? So just comment it, and you're not planning every time you run it to have it installed again. So that's it to start with. Now let's load US data CSV, just using read delimited, telling them we have a header for our variables, and it's separated by comma because it's a comma separated value. There you go. 209 observations of 4 variables. Let's click. There we have observations from 1954 quarter 3 until 2006, I think, quarter 3. We have both interest rate, GDP, and inflation, consumer price index, CPI. We will be working with these 2 guys, but for the question 1, we'll be working with GDP, okay? That is it. So first, dates. Let's extract this guy. Oh, we're taking this here, obs, you will see, but we are transforming as year quarter. So let me show you a little trick to when you want to understand what's going on. First, let's select just the my data, and then let's click run. Run is behind whatever I have in the screen. I'll press Control Enter. Look, we have year for the first 4 digits or algorithm, I don't know, letters, and then quarter for the next 2. This as year quarter is coming from zoo, if I'm not mistaken. Look, as year quarter, zoo. It makes a little bit of a translation. So it will be looking like that. It has some, it's saying it's a string of characters. So you have the quotation marks there, and it's adding a little space in between both. So if I run this, the whole line, date receives what we see there. It's not showing any values here, but if you click and print date, it's exactly the same. All right. Why is just receiving GDP? So if I run, you can see already the values in there. R will be receiving our interest rate. That's it. Now, the first thing they ask is plot the observed time series and comment on potential trends. Let's have a look. Plot. Does it look like there's a trend? What do you guys think? Please send me in the chat, or maybe a thumbs up or a no, if you don't think so. Yeah, looks like you can see one thumbs up already. It seems like when we're dealing with our ARMA models, remember we were trying to look if it was a stationary. It definitely doesn't look like a stationary ARMA in here, or a stationary time series, stochastic model. So there is a chance there is something moving it up. Like the equation we're choosing should consider that, okay, this is not a stationary. How can we deal with that, right? And we need to, given it is going up all the way, we should check if there's a chance that there is a unit root in this time series, or this stochastic model. So one thing I wanted to show you what a unit root looks like when you're doing an ACF. Look at this. It's a pretty large. Remember, when we're taking an autocorrelation function, the first one is always 1, right? Look how much we have as the first leg. It's almost 100% too. So we're in a dangerous zone. For the second one, it's way above 90. If I plot it like that. Let me put a plot equals to F. Look at these numbers. They're really high numbers, very close to 1. So this is one way of looking. Well, there's a chance there is a unit root in that, because our current observation, let's say YT, it's really correlated with the next one or the next few legs, I would say, right? Very high values, very close to 1. So, all right, I just wanted to explain you a little bit the risk of having a unit root. And if there is a unit root, you would see this previous plot. It's just walking by itself. The rest is not important. Or maybe if you put it forward, it would explode and go up to infinite or something. If you try to forecast for the long term, that's the risk when we're doing this one. Maybe if we have a unit root, we would still be able to forecast for a short period, but definitely not for the long run because it goes all the way up. That is it. All right, we've plotted. Let's go for the next one. Plot the observed. We've done. B. Construct an adequate set of augmented Dickey-Fuller regression models. Okay, let's go to the code first. Then I go back to that interesting slide. First, we will have, estimate the ADF regressions for different values of B. One important thing to realize, when we're doing this ADF, we're only doing it to test for a unit root. This all happens before we do those things we were doing before with the ARIMAs. The ADF is just to test for the unit root. And we don't need the moving average at this point. We will only look at the autoregressive legs. We will look at the constant we will look at the trend, and we will look at the AR legs. We will also look if it's differentiated later on, but that's it. Will we? Maybe not. But for the ADF, this is what we use. So let's go. First, TT will receive the length, the amount of observations. So it should be 209. ADF estimates will receive a list of models. So to start with, this is just an empty list. IC is the same matrix. Let's say we're using the information criteria matrix, but this one will be for our ADF. Okay, the first one. So it will be a matrix with 30 rows and 5 number of columns, 5. Could you have done it differently? Yes, you could. Instead of having this 30 rows, if you want to automate a few things, you could have another variable multiply. From 0 to 9, it's 10. Then constant. From 0 to 1, it's 2. But when it's 1, it will have both with and without trend. So this is actually, there will be 3 guys there. So 10 times 3, 30. All right? This is where this 30 is coming from. So let's create the IC. Just, let me put the mouse in the right place. Just an empty matrix. Then probably we're giving it some nice names for it. Now we know if the constant 0, 1, trend 0, 1, amount of legs, autoregressive legs, and then our score, our information criterion for AIC and BIC. Then I0 is just the index of the matrix. Each model goes to a new one. So let's just create this I equals to 0. And then we're going to our for. So for the first one, we have constant equals to 0. Then we will try models with P from 0 to 9. Then we will have constant equals to 1. And we will try once again from 0 to 9 in autoregressive legs, but we'll do 2 things when constant equals to 9. Okay, so we will get that. So first thing we do, I was 0, so let's add 1, and I becomes 1. In this first run, we are first generating the model. So ADF est, the first row, because I now is 1, will receive an ARIMA. And pay attention what's going on here. Diff of y. So we are already using a diff of y here instead of y itself. And you notice that in the ADF model, we are using a delta y instead of yt. So already talking about change. Okay? So that's why you see the diff in there. Then xreg of yt is receiving kind of the time series. Is receiving. My point was this little t here. So we're telling them that time is the one that is going to be used in here. So that's what's going on a little bit there. Xreg. This, once again, this code, you can use pretty much the same way. You will change very few things for your assignment. So you don't need to worry exactly what it's doing. It will work for you, okay? Order. So now the order for our ARIMA, for now, will be 0 in the difference and 0 in the MA, right? So in the integrated, I integrated or diff, 0, 0. Just the legs, P legs, we will have that. So autoregressive legs. What is new here? We have this include mean as logical constant. So include mean is the one that will be looking if we have a constant or not. So if we're not considering constant, we're looking at this model. If we're considering constant but not trend yet, we're looking at this model. So that the test is now choosing between these two. And then I will get to this one in the next few lines. Next one, include drift. This can get a bit confusing here. It's just because of the algorithm, the way that we're doing things. We're saying include drift equals to false, while in here we're calling the constant a drift. So I don't want you to go around too much. I remember last year myself getting a little bit lost. So why? What is the drift? The drift is this guy, but for our algorithm, particularly because we're already going from a difference here, this is receiving a false. Okay, so I think it would be a good idea not to mix these guys with the drift from that we look in there. Let me try to show you also. Today we have a nice amount of time, so let's explore as much as we can these things. There is include mean, there is include drift, there is include constant in there. And you will see that they have different behaviors. So depending if you're looking at differentiated data or not. So should a RIMA model include a mean term? The default is true for undifferenced series. So if this wasn't a difference, the default would be true. And the default is false for difference one. The same you'll see here for this include constant. It has a different behavior. So I believe if you try to get too deep into this one, it can get a little bit complicated. So I think for our level, it will make your life easier if you just trust the model, trust that it's working. Otherwise, if you want to invest time, if you're someone who wants to research it further or work with it, then make sure you pay attention to these things. And remember that this RIMA we're running already on a differentiated model. And yeah, you'll have different things in there. Okay. So, all right, a little bit of detail there. But all right, we're generating a RIMA. And now we're going to store the values. So we're storing if constant is 0 or 1. For our first run, it will be 0. Then we're storing another 0, which is, I think, is the trend. Yes, if we have a trend, it will be 0 because for this first run, we're considering that trend doesn't exist. And then we'll store the number of flags, the score we have for AIC, and the score we get for BAC. Pretty simple. As we used to do before, we have the const and trend different now. Now, if constant was 1, we want this third equation where trend is also 1. So we have a constant and we have a trend. So now this second part of the code, we'll look at this case, yes. So first, we went through the 9 in there, close this for is closed. Now, if constant was 1, I want to know we will have another 4, also an increment of I, because we're adding a new row. So we have no constant, no trend. Then we have constant, no trend. And now we have constant and trend, right? So another row. To estimate the RIMA model, these are pretty much the same. The order is the same. Include mean as logical constant. Same thing, but include drift. Now it's true. Include drift is true. So for our differentiate model, what we're calling drift is actually this guy here, which will be a little bit confusing. But in general, the drift, when we're looking at the equation, it's this guy. This is the drift. This is the trend. Also, when we do the ADF test, this is how it look like. Okay, that's how I interpret. After that, we store the same thing, but you notice that the trend guy, now it's a 1. So I don't think I have run. I ran it, but let's run and let's have a look. It looks a lot of an ace. Let me try it again. I might be missing something. Okay, yeah, I was missing the ADF estimate here, as you can see. Without it, things don't work. Let's run it again. Much better. So our IC has all the models. So remember, we started with 0 constant and 0 trend, and from 0 to 9 legs. Then we wanted constant, but no trend from 0 to 9 legs, and then constant and trend from 0 to 9 legs. All right. Now the next 2 lines will get the top 10 from each, from AIC and BIC. It's the same as sorting it here. So you will see for AIC that most of it, all of the top ones have a constant. So assuming there is a constant, gives you better AIC scores, let's call it, then not considering there are no constants. And then same for trend. BIC, on the other hand, has a few zeros in there, but in general also thinks that having a trend, it's better. Let me see what my slides are showing, because I think I highlighted the models then. Yes. What we're going to consider, because they are relatively similar, we're going to consider the top 5 models in the BIC, which are also 5 of the top 7 in the AIC, to move forward. All right. At least to move forward, what is the next step? To check the residuals, right? Oh, no, sorry. We're doing an ADF test. No, yeah, it's right. It's also checking the residuals. All right, so let's, maybe I should follow the slides not to say wrong things. Get the top 10. Does it need to be the top 10? Is there a secret number for top 10? If you've been watching the live lectures, you learned that no, it doesn't need to be the top 10. And today, I want to start giving you a few advices for when you start doing your assignments on how to deal with a few things that might pop up to you, give you a few options of editing the code. I think I'll leave it for exercise 2. So stay watching for the second part, like second half of it. But for now, it won't be necessary because we get the top 10. Then look at here, adequate set will be as matrix. We're getting, let me run first. So we're getting the ICBIC, so this list of top 10, and just getting the 5 first rows, as I showed you on the slide, right? So as data frame, then it's doing an arrange, and this arrange will have constant first, then trend, then P. So when you look at this guy here, we have 110, 101, 112, 102. It's kind of out of order. When you look at the adequate set, this is the first one, adequate set, you notice that we have all ones here, then 0, 1, 1, and then in order 1, 2, 1, 2, 3. That arrange is just putting these guys in order, okay? And this is what it's saying. First, organized by constant, it's the top organization, then trend, and then P. And then it ends up putting it as matrix. Then save the index, saves the index from each of the 5 models. This adequate set index, we are saving it because when we call that function, we're calling from this ADF estimates. So have a look at what we're getting. Adequate index 12, 13, 22, 23, 24. If I open ADF, let's look for 12. ADF 12. ADF estimates, right? And then I go to order. There should be an order. Model. No. ARMA. Is that what I want? Coefficients. Oh, should We don't have for this ARIMA with a capital R. We don't have the order to see which one is 12. Okay, I will look in the somewhere else. So 12, I see row 12, 101. Do we have it in our adequate set? 101. So that's a little bit what's going on. Now we're checking for residuals to see if we're violating the assumption that the residuals are either white noise, or if the residuals for the Young box test, if there's some autocorrelation on the residuals in the first 10 legs. So this is the output we get. Remember, what we usually pay attention to is this guy here. So as you can see, for the 5 models, we have 0.48. So we're not rejecting the null hypothesis that the first 10 legs are not there's no autocorrelations in the 10 legs. And it's important to pay attention what is the null hypothesis for each test. So Young box test, rejecting is a problem, is bad for our model. And you will see in the ADF that the objective is to reject. Rejecting is kind of good for our model. Okay, so let's pay attention. This one, by not rejecting, we're not rejecting that. I think it's easier to explain that the hypothesis that the residuals are white noise, but it's a little bit different than that. Eric was explaining the lecture today. It's actually there is autocorrelation. If we reject, it means there is autocorrelation in the first 10 legs. As you can see here, look at the first 10. They are fairly, well, this is 100. Let me go back to 100. Okay, 100. You will see the first 10, they're fairly far away from our statistically significance. Maybe 5 is not too far away, but they're very happy with the results. So that's where you're getting your 0.48 from. And the same for the other models. We're very happy at 5%, at 10%, 20%. I think we're happy even at 40% if nobody uses. But yeah, we are all good with these ones. So right now we have the models. These are the ones we get. Let me move this out of the way. Now, let me go to the slide. These are the 5 models. We check the residuals, implement the augmented Dick-Fuller test for a stochastic trend, and draw inference regarding integration properties of YT. So now that we have our best ADF models, ADF estimates, let's run an ADF test. And look, it is very simple, just ADF test. This is coming from the ATSA package. Oops, test. And you just plug in the data as an input, and it will run for you. Let's have a look. Augmented Dick-Fuller test. T. First, type 1, no drift, no trend. In this case, we are rejecting the null hypothesis that there is unit root. But this type is not interesting for us. Why is that so? It's not, we don't have any model on that one over there. And let's have a look why we don't have. Let me try to put both things in the screen. Where's our adequate set? I will click this little guy there. Nice. My thing is getting on the way. Oh no, Zoom is getting on the way. That's annoying. Let's see if I can move it from here. Right click, maximize. Nice. So yes, it worked. All right, this is what I want. Remember, type 1 is no drift, no trend. So type 1 would be 0 and 0. We don't have any 0, 0 in our top 5 models or our adequate set. We only have type 2 models, so with drift and no trend. In that case, we have a 1 and 2 legs. So we're looking at leg 1 and leg 2. And look what we get for both of these cases. We are not rejecting the presence of unit root. Very important for your assignment and everything. We are not saying there is a unit root, but we're saying we are kind of not rejecting. So usually what we say is, this is not empirically distinguishable from a unit root process. Or if I said it wrong, double check, make sure we're saying exactly the same words, but yeah. This is not distinguishable. So if we reject it, it would be distinguishable, but this is not empirically distinguishable from a unit root process or something else. Okay. That's the case for these two guys. For the other three would be 1, 2, 3. Also not, a little bit lower number, but it's still far from rejecting at the 5%. So this is what we're doing here for the ADF. All this is happening before our ARIMA, creating this ARIMA. So what are we going to do now that we realized this is not empirically distinguishable? What can we do? We can try to work with the same data, but in differences, or the delta YT. So implement, this is what we got. We didn't have anybody here, just these two guys. And you see, since only type 2 and type 3 specifications are in our adequate set, we ignore the output related, So now the official way. We conclude that the process is not empirically distinguishable from an integrated process with a drift. Drift and drift. And possibly linear growth, possibly in here. Okay, this is one way of saying it. This integrated process, or similar to the unit root, it's talking about the same thing. And let's go. Now D, repeat parts A to C for a different series delta YT. Yeah, could you recap on the drift logic in the code again? Yeah, sorry, CNight, I'm just seeing your message now. The drift logic. I will do it for now. We're doing the difference differentiated. Yeah, sure. Yeah, sorry, I'm just seeing the message now. Let's go again. See, we did it here. I try to keep the same code as we have in the answer in here. So this will be in the PDF of the official solution. Okay. D, repeat for differenced Y series. So first, the TT that we had before, you will see it's the same TT, but it's the length. Instead of Y is the diff Y. And remember that when we get the difference, it reduces by 1. So I would expect it to get a 208 now. So you see 209 before. Let's run for diff. Becomes 208. Okay. This is just to use at the XREG later. ADF. Estimates, so augmented Dick-Fuller estimates, but now with the different data. You notice, like, I'm always going to say differentiated This is tricky. Differenced. That's not something we say a lot. You won't have an official answer a plot, but I like to show you the difference. When you take difference, look at how it looks. I will run the previous plot again so we can have a look at it. Where was my plot? In here. Look at that, going up. But when we take the difference, now it looks way more stationary, doesn't it? Look at it. Going there. Is it around 0? Probably not. It looks like it's a little bit above 0. And that's what this a little bit above 0. It's what makes this guy move up as in a kind of a trend or constant. But it's in our linear regression would be the beta 0. It's the average is a little bit above 0. Okay, but that's not what we're doing. That's not exactly what we're doing right now. I just wanted to show you that the plot for a differentiated by differencing, it starts becoming more stationary. That was my point. Sometimes, very rarely, you need to difference twice so that it becomes stationary. But well, let's go from here. Maybe I'll also add the ACF for this guy. Let's have a look. Remember the previous one. Let me run it. The previous one, whoops, this is without a plot. We had numbers very high, very close to 1. Now, let me add this ACF. I will share this code. I'll update the code later. For the difference data plot. Now, I'll add it here, but instead of y, we have diff y. First, without the plot, with the plot, sorry. I'll maybe just change it to true. Look at that, how different, hey? The other one was very high until the end. And this one already falls considerably. Including, it has 2 statistically significant lags. And then for the numbers, you can see clearly that it falls dramatically. The number 1 lag for lag 0, we have 1 as usual, and then it falls to already 0.29 and 0.17. So the chance that we have solved the unit root problem, you can get a little bit of indication here. You won't conclude just by looking at it, but I wanted to show you a little bit how difference behave. All right, let's move on. Okay, now we're creating a new IC matrix now for the difference data. Also 30, number of columns 5. Call names. And then I initiate the I0, our index that will run. So let's have a look. IC is empty, the same thing we had. Oops, not IC. IC diff now. Empty with the columns. It's kind of identical. In this one, you will have, it will be pretty much similar. So we have constant yes and no. So, or better, no and then yes. For P, once again, from 0 to 9. And the increment index, right? We will run this one considering no trend, even if we have a constant or not. But when we have a constant, we will run it again, considering then a trend. So you will notice some things are similar. So this is 1 and this is true. The previous one is 0 and this is false. These are indications that we're not considering. The slide, this slide here. Okay. Ooh, not what I want to. So when constant is 0, when constant is 1 without the trend, when constant 1 with the trend. Okay. Let's try to dig a little bit deeper, as CNET asked. Let's try to dig a little bit deeper on the drift. I'll be honest with you. I don't know this 100%. I'm not 100% sure on it. I never explored it that deep, but include different. Should a Riemann model include a linear drift term? For example, a linear regression with a Riemann errors is fitted. The default is false. So in this one, we're not considering the linear regression. So when we look at, remember that I draw a linear regression here. So first, we're considered just the constant. And sometimes if it's different or not, it's when you call it mean or when you call it constant. You'll see we have both here. And then the drift, they are calling it the drift when you do a regression. So you have this delta t in there. But so this is the ARIMA model, the ARIMA function. That's how this function is calling our trend. Okay, and we are calling it a drift, the A0. So this is a drift. And now they are not the ARIMA, but the ADF, augmented diffuller. We're calling this guy a drift and this guy a trend. Now I'll give you what I assume to be the case. We are dealing with diffs in here. So I believe because we are dealing with a difference in there, this guy actually becomes something else. It becomes a drift. I assume that might be the case, but I think at this point, the important thing is to accept that it's doing the right thing. It was implemented by Eric. So yeah, this is why we might have a little bit of a confusion by names. But for us, we will follow the theory and we'll follow the ADF. So the drift is the constant and the trend is the thing multiplying t. All right, see, Nate? All good? Fantastic, amazing. All right. So we're creating the same thing. Notice that now everything we're doing, it's talking about a diff of y. But since we had a diff of y in here, now we have a diff of y. You will notice that one nested inside of the other. Also, the x-reg here will be diff of y, and the rest is the same. Same guys in here, but for the rest is the same. So important thing now, what we're dealing with is this guy now, a little bit more stationary, right? So let's run each of the lines. Plot ACF. Did I run it? Okay. Yeah, I run it, just came down here. Now we're creating ICG, call names, I0, and I'll run the whole thing. Cool, done. Does it need to be 0 to 9? No, you could try 0 to 90. A warning, if you watched this, the lecture this week, yesterday, you would know that the longer the lags, the longer it takes to process because it becomes more and more complex. You have loads of coefficients, but it could be more than it. Constant, it has to be 0 or 1. It doesn't, it's a yes or no. And the same for the trend. But lags could be more if you feel some indication that it's important. We will deal with it later. Okay, now we have the whole thing. So IC diff, all the guys are there, all the 30. Let's organize. Look at that, constant, not so much trend anymore. And then BIC, constant, a few trends, but not that many. Let's run top 10 models. And now let's get as matrix. Once again, this is more interesting. Now the top 5 models of AIC and BIC are the same. Let's go to my slides just to show you. So now we're running this guy, and look at that. Oh, a little bit further. D. Yes. Look at that. They're just in a little bit of a different order, but you will notice that these top 5 are the same. And in fact, you will find all the others. 112 is 112, 103 is there, 105 is here, 113 is here, and 104. So the top 10 are the same. It's pretty cool. It's pretty good that we're getting the same scores. So we know we're confident we can move on with these 5 models. And see, so adequate set diff, just getting the top 5 from the BIC, okay? And arranging it the same way we did before. Adequate set diff, click that, well organized, so 0 and 1s, and then a little bit of order here. You will notice that now, instead of having lags 1, 2, 3, it seems like we're looking more at lags 0, 1, 2, and the trend is just 3 of them instead of 3 without trend and 2 with trend. Previously, we had adequate set without being diff. We had 1 extra, and we were not dealing with 0 lags. So I just pointing out that when you take the difference from the data, you might start getting different models, and you'll see some pattern. You start identifying a few patterns when we deal with different data. Close. Now, once again, taking the index of this guy. So when we know that it's models 11, 12, 13, 21, 22 from this ADF estimate diff list. Finally, let's check the residuals. Boom. It will be processing. Let's have a look. As per usual, we'll have a look in here. You will see that we would not reject this this hypothesis of null hypothesis of not having autocorrelation in the first 10 legs in any of our models, not even close to rejecting. So these residuals look like kind of a white model, a white noise, sorry. And that's it. So we're happy with the 5 models. Let's run ADF test, but now for the differentiated data, differenced data. Look at that. Now that we have differenced data, we are rejecting with a very, very low p-value for all the models. Let me open adequate set diff. Can I make the magic again? Yes, nice. Let's have our models here. Which ones are we looking at? Constant, for sure. So forget about type 1. We still look having a constant there. Then we have with no trends, we're looking at leg 1 and leg 2. So leg no trend, leg 1 and leg 2, both okay. So for the difference data, it seems like we are rejecting the null hypothesis that there is unit root. So rejected. So we can say pretty much that's what we can say, I would say. And then for having a constant and trend, we have legs 1, 2, and 3. So these 3 guys here reject for all of them. Okay, these are this is the adequate set. I'm opening the wrong one. Am I? Did I? Oh, I think I opened the wrong one. Sorry for that. That makes more sense now. Sorry. So the only difference is that we are doing for no trend, it's actually the top 3, but the results are the same. So 0 legs, diff, yeah, for difference data. 0 legs, 0, 1, 2 legs for the no trend, and 0, 1 for the one with trend. Apologies, I opened the wrong one. All right. And that means we are okay with this this set. So let's move on. Look at that. Top 2 guys here, top 3 guys there. So our unit root is rejected at a very small significant level for all specifications. Hence, the differenced process is empirically distinguishable from an integrated process. Okay, the differenced is empirically distinguishable. The levels that non-differenced, it's not. Calling your attention about it, because from memory, I think my head was spinning when I was trying to put these things together. Interpret the overall findings in part C and D, and look how we interpret. Since the data in levels, GDP, this YT, is not empirically distinguishable from an integrated process, but the differenced version of it is, so it is distinguishable. We conclude that the GDP data in levels is not empirically distinguishable from an I1 process. I1 integrated process, which is the process that has a unit root. Yeah. Remember, however, that we did not find evidence that YT being an I1 exactly. So we can't say we find that this is an I1 or we found the unit root. We just say it's not empirically distinguishable. And I apologize for repeating it, but it's something that commonly people would confuse and go the wrong way. Okay, that's how we interpret. Finally, did the whole ADF found the unit root or not? Now we're going to do the ARIMA process that we usually do, or that we've been doing this last few weeks. Let's go. F. Now they're explaining here. Once again, we will consider from 0 to 3 lags of AR, 0 to 3 lags of MA, and we will consider the differenced data. So D in our ARIMA model, the integrated, we will consider not the integrated, so data in levels, and we will consider integrated model, so the difference of the data. Remember ARIMA, the one in the middle, the D? So that's what we have here. And then you will see there will be 96 models, and I will explain you why. It will be a few nested fours, so one inside of the other. And let's go line by line. This is a little bit of the same, so I didn't add a lot of comments, but it's pretty clear here. TT gets the length of Y. We're using this TT, look at the xreg, I think once again, and also for cumulative sum. We're doing it manually. Not xreg, we're doing the thing manually. Look, it actually, sorry. So xreg is using x, and x is using this TT, doing the cumulative sum. ARIMA estimates receives a list. Once again, it is an empty list of ARIMA. The same way as we did before. I see ARIMA now will receive a lot of things, and I'll put the column names to explain. I receive 0. I is just the index for the rows. And before I run, look at that. I see ARIMA. So now we will have D. Is the process integrated or not? Are we putting a 0 or a 1 in the middle of our ARIMA order? Then constant, 1 or 0, 0 or 1. Trend, 0 or 1. Then AR lags P, how many? We will be analyzed from 0 to 3. Then MA lags from 0 to 3. Then we take the AIC score, and then we take the BIC score. Okay, so we're extracting a lot of information from our ARIMAs, and we will save our ARIMAs in the ARIMA est that is in here. we create an empty list. That will be a list of all the 96. Why 96? Let's go through the numbers here. 4 squared, it's pretty much 0 to 3 legs for the RA combined with multiplied by 0 to 3 legs from MA. So there are, since we are also considering 0, so from 0 to 3, there are 4 options. The same for MA, one times the other, 16. And we have this 2 times, which is the 2 from differenced. So we have running everything for data in levels, D equals to 0, and everything for data in difference, diff, which is D equals to 1. Then, this is a little bit, I don't know why it's done this way, but it's pretty much, they could have multiplied 2 by 3, because the 3 models, as you might remember, is 1, no constant, no trend. Second, constant, no trend. Third, constant and trend. All right. So this is, if I would do it 2 times 3, or I'll put it in a different way, but pretty much 6 times 16 is 96. And then the 7 columns are all the information we have in here. Now let's go. Let's run this 4. This is taking a tiny bit more time. And we will have all of them. I see a Riemann. Look at that. Start with all the ones with 0. So data in levels, 0, 0, and then starts 0, 0, 0, 1, 1, 1, 1, and then 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So you can see the 4 loops happening in order here. And it goes all the way down to, ooh, look at this. This is interesting, and we will explain how that happened throughout the code. All the way down to 96 with it is difference, there is a constant, there is trend, and we're using the maximum legs for both. All right. All right. Let's choose the top 10 models now. Boom, boom, same way as before, but now tricky and lovely way of choosing the intersection between both matrices. Look at this. We're using intersect and putting as input as data frame IC AIC ARIMA, and then as data frame IC BIC ARIMA. So these will automatically choose the top the intersection, like the models that are in both. So when I run it, and definitely use it in your assignment if your criteria to choose is the models that appear in both. Where is it? I see int ARIMA. I see int ARIMA. So we have 4 models, 4 ARIMA models selected for this for our adequate set. So look at that. No difference. So data in level, all of them with constant, all of them with the trend, and then ARMA 30, ARMA 21, ARMA 20, and ARMA 12. But these guys are pretty much the same, okay, for the ARIMA. And there is quite an explanation here. And we will do another thing. Remember that we found there was a unit root for our, oh, sorry, I can't say that. We didn't find there is a unit root, but it wasn't empirically distinguishable from an integrated model. So there is quite some indication we should be using differenced data too. So ARIMA with a 1 in the middle. When we got to the difference model, then we were not distinguishable from an integrated model. We were distinguishable from an integrated model when we're using the difference data. So that one looks more like a stationary data than the first one. So we will manually add these models. So look, what is happening here is the following. Adequate set ARIMA. We're taking it as matrix and doing it in a range, but we are getting the IC int ARIMA this guy here. I see int arima, there's 4 models, but we are adding with a row bind. So we're putting a few others in the bottom, which is the BIC 1 and 3. So BIC, IC, BIC arima. Line number 1, which is this is differenced, and line number 3, row number 3, which is also differenced. So we're adding these 2 guys to our adequate set, so we can have some forecasts that are also difference data. So let me run it, and you will see the magic. Adequate set arima, adequate set arima. Look at them there. 1 1 1 1 0 1 0 0 2 0. Let's check. 1 1 0 1 0 1 1 0 2 0. All right. Let me close it. That's it. That's what happened here. Finally, we're doing the match just to get the indexes. If I run this line, adequate index arima, adequate. Oh no, just here, adequate index arima, 30, 36, 34, 42, 73, 81. That's it. Once again, check residuals. And let's have a look at the scores we have at the p-values. 0.488, 0.62, 0.535, 0.64, 0.51, 0.57. So we're not rejecting the null hypothesis of white noise, or in this case of not having autocorrelation in the first 10 legs. It will call your attention some long legs on the 20. This is at least caught my attention. This, in this case, model 300, slightly crossing. Oh, it's crossing for quite a few models. And one thing that I would, okay, it's now it's combining with the previous ones. One thing that you will notice, if you run a Young box test considering 20 or 21 legs, probably these scores will be considerably lower because we have this high correlation there. But for the ones that we're running right now, it's just 10 legs. So it's just considering this ACF until here. All right. That's what I wanted to add because Eric was explaining it during lecture. I thought would be important to add. So happy days. We're happy with all our 6 or 7. 1, 2, 3, 4, 5, 6 models. And yeah, and we would proceed by generating forecasts with it. Not something we're going to do today. Do you guys have any question about it before we move to question number 2? This is, oh, you see the models that we chose. I don't see anything in the chat. So that's it for GDP. That's the whole process that we do. Now for number 2, instead of looking at GDP, we will be looking at interest rate. And we'll redo the whole thing, but I will go a little bit faster now that we explain item by item. What I would like to add to you is that some things I won't be happy with everything that we're looking at, and maybe give you some options on how to change the code, how to adjust a few things that you might need to adjust during your assignment or not. But yeah, it will give you a few options. So let's go. Number 2. Once again, let's plot our interest rate. Look at that. Slightly different from what we had before. Slightly different from we had something growing all the way. This one, it's not growing all the way. It goes up, then it goes down. It is definitely all the time above zero. As you know, interest rates are usually above zero. Sometimes you might be dealing with the zero lower bound, etc., some macroeconomics terms, but it tends to be above zero. All right. Another thing, let me add something here. Let's do an ACF just for fun of R. Does it look like it has a unit root? I would say at least a little bit, because look at how high the first leg is. It's definitely above 0.9. So if you do a plot equals to false, let's see, 0.955. Look, it's not a 1, but it's so close that we possibly should be a little bit concerned about it. All right, I'll put it on hashtag ACF of interest rate. All right, let's do the process again. So length for the XREG, ADF estimate. What would a unit root graph typically look like? Good question. Can I say what it wouldn't look like? It wouldn't look like a stationary plot. It will be a lot of plots before. A unit root plot would rarely look like this. This looks like a stationary thing. So it is going around one line, and it has relatively constant variance. This is questionable. Maybe there's a lot more variance before than it has after, but a unit root probably wouldn't look like that. It looks more like what we had before. For the GDP, this is this is clearly a linear. If you do a linear regression, you get very small variance because it looks like a line. And it could also look like this guy. The important thing here, C-Knives, is that we are not taking our conclusions from the plots. I just want you to have like a little bit of an idea. Oops, is that? No. Just a little bit of an idea and look at the things. Can you see? It doesn't look like it's going around one line, but we can't also conclude that this is for sure a unit root. We need to do the proper test. All right. Amazing. All right. So TT, ADF est, IC, the same information criteria matrix, column names, I0. So let's go. We're doing the same thing here. Exactly the same algorithm. There's nothing different. The only thing is that it's an R instead of a Y. Other than that, same things. So let's have a look what we get. 4, run, then AIC, BIC, then let's find the intersect. Now we're fancy. We're using, particularly, we go straight with the intersect. How many models do we have in the intersect? IC int. Only 3 models. 107, 007, 106. Are you happy with 3 models? If you are, move on, continue with it. If you're not, let's add a little bit of a trick here. Do we need to have the top 10? We could consider more than top 10. Look at what adequate set is just taken as it is, and index. All right. Adequate set is just taking this 3. But let's pretend I'm not happy. One thing you could do is, like, instead of getting the top 10, I want to see the intersect of the top 15 instead. Look what happens. Boom, boom. Then I run intersect. And now my IC int has 6 models instead of 3. This is something that might be useful in your assignment, depending on the data you're dealing with. You might, when you run it, you might have just too few models, and you want to try a few others. This is one trick, increasing the top list that you're looking at, and then you take the intersect, okay? For now, I'll come back to 10, so we can continue the analysis following the standard thing, and let's check the residuals. Well, okay, let me expand this guy, and look, for the second and third, we have very high values, so 0.54, 0.68. So this is for the 700. This is for the 7002. It's probably one with the trend and one without. I see int. Let's do that little thing again. Let me move. Once again, let's do it down. Maximize, move. Well, so the last one. Sorry, it's organized now. So I should have open adequate set. Adequate set. Expand. There it is. All right. So last one will be this 007 without a constant and without a trend. It's all right. This one will be the with constant, no trend, and 7 legs. Once again, it's the ADF that we're testing here, so we don't have a MA or consider anything else. But for this Young box test, the first one, it's a little bit closer to the 5%. Let's have a look at the plots. I would like to show you. We are considering the first 10 legs. So this is for the last one. This is for, sorry, this is for this one. Very comfortable. This is for this one, also really comfortable. You can see up to leg 10. It's all good. But this gets pretty close to 0.5. What's going on here? Look at this guy here crossing the statistically significance. I think this is a really good example of when Young box test fails. So you see this guy crossing. So it wasn't enough to say it's not we're rejecting, but it causes a little bit of a concern when this happens. Okay. So this is probably the motive why this number is much closer to 0.05. Yeah, just wanted to call attention to it. All right, let me close this, guys. Close this one too. Let's keep going. We have our adequate set. We check the residuals. So as with levels, residuals look okay, but with some indication that longer leg lengths should be considered. And we will run ADF test. For I'm sorry, we are here, in fact, not there. So residuals look okay, although some ACs exceed 95% confidence intervals, like this one, very slightly, and at larger legs. Oh yeah, and then at larger legs we have this on the 16, and here, so leg 16. For robustness, we might add a few longer legs into the adequate sets, such as P equals to 8 and 9. All right. We are going. So now we're going to run ADF. You saw that we have 6 and 7 legs, but our original ADF without this thing here shows us just the first 0 to 4 legs. So what we're doing, we're adding this argument. Look, consider legs until 10. Look what's going to happen. Now we have we are considering more legs going until 9, 0 to 9, and 0 to 9. And what are our models again? Let's click on the adequate set. Let's move it out. I'll have to do all the trick again with the thing. maximize, then move. Now I will expand this guy and look at that. Constant 0, trend 0. So we're talking about type 1 for that one. And then 7 legs. It would be this line here. We are not, it is not empirically distinguishable from integrated data or process, integrated process. The other one, 0, 1, 0, 0, we have both of them for 6 and 7. 6 and 7, also, they are not empirically distinguishable for an integrated model. So there is some indication that there might be a unit root. That's why we're going to deal now with the differenced data. Just checking what time it is. We have time. So for following from here, you'll see there's quite a long explanation. Only type 1 and type 2 specifications, This is the 9th ranked specification, etc., etc. Now we're moving to the differenced one. Once again, let's plot. Boom. Now the interest plot, now that we're differentiated, it looks a little bit more stationary. Clearly not here. The variance is not uniform, but it looks a little bit more. So we have a constant, and it seems to be around 0, I would say, maybe a little bit different here as a mean, and variance very low, then getting higher, then very low again. So let's start running. Let me see, no questions at the moment. Let's continue running the algorithm. Create the IC diff as we did before for GDP. Run the whole thing. Do we need to pay attention to anything different? I don't think so. It's exactly the same, just with an R instead of an Y inside. So let's get our adequate set. Look, now we do an intersect of AIC and BIC. IC int diff. IC int diff. We have only 2 models now. I would say, and there's no right number of models for it, but since trying to fit an equation, that's what we're doing here, trying to fit an equation to a data, it's never a perfect process. I would suggest maybe 3 or more models to be considered. No hard rule on it, but if you're doing a forecast with just 1 model, it means you're really sure that that is the true stochastic process. I would say it's always a safe bet to have maybe 3+, maybe 5, or maybe if you want to be very comprehensive, 9, I don't know, but 2, maybe, I don't know, maybe not good enough. All right, unless the 2 have like AICs and BICs that are way better than all the rest, then maybe they are really relevant. All right. Only 2 in the intersect. Are you not happy with 2? Look at the trick. Now, I think first, before I do the trick, so there are only 2 specifications in the intersect, both with no constant or no trend, p equals to 6 and 7. Overall, both AIC and BIC favor specifications without a trend, and AIC generally favors larger lag lengths, whereas BIC yields a more dispersed ranking. Look what they're doing. Just adding it to the set, then getting the index and running the check residuals. I would like to change, if I would like to change that, I would put 15, run. How did my intersect change? IC int diff. I see now I have 6 models. Now we're considering 4, 5, 6, and 7 legs. And now we have with 1 constant, always without a trend for the diff. You will see that by taking the difference, usually there would be less in the trend, as you probably noticed. Because sometimes by taking the difference, you're taking the trend off. That's it. That's the difference. If we did all of it, let's continue with the 10 for now. And finally, check the residuals for these two guys. We get a 70% and 59, 0.7, almost 0.6. So we're not rejecting the null hypothesis of white noise. Finally, ADF test for this. In this case, 6 and 7 lags for only for 0, 6, and 7. Only for type 1, so no constant and no trend. So let's go there for type 1, 6 and 7. Now for the difference data, it's not, it is distinguishable from an integrated process. So that's it. It's a little bit what we found from the one before. And that's how we analyze. Since we have a little bit more, and just this is it for this tutorial. Let me put all of this online in the, oh no, it's all there already. You guys copied the code. Just for a difference, now I'm adding a little bit. If you don't want to continue, you can watch it later. You could be analyzing a little bit more the other models that we found. So I will put a 15 here and a 15 there. So 15, 15, now we have 6 models. Let's see what changes. Adequate set, diff now has 6. Excellent. Index, let's check the residuals. You will notice that, in fact, now that we add more models, these first 3 models, we would reject the white noise hypothesis, null hypothesis. So although we added these models, let me show what they are. Adequate set diff. They are 004, 005, and then 105, one with a constant. These guys, we are rejecting the null hypothesis of white noise. They are violating that hypothesis. So we're probably dropping them from the group. But we're still counting on this 106 there, this guy with one constant. So let's have a look at the ADF, what they were saying about this type 2. So sorry, a constant or a drift, but no trend. And was it 6? It was also, it's not, it is differentiable from an integrated process. So yeah, it is also a good model. And you could do that with your assignment. You could consider a little bit more, a little bit longer lists. You could also consider longer lags. So whatever, this is the ADF, it's going until 9. Maybe perhaps you want to do until 15 or until 20, because these are the models that make more sense for you. So you would test it there. The same way that you could do it for your ARIMA. Remember the ARIMA we were doing? We didn't do it in question 2. We just did it for question 1, because it tells us not to, like, do not need to do part F. We could, instead of using from 0 to 3, you could 0 to 9 or 0 to 20. But I did it earlier today, 0 to 9. You have to adjust the size of your IC, and it takes a long time to finish. One more thing that I forgot to say, it is in the comments here. We are using, when we're doing this ARIMA estimation, there is a chance that some values will go wrong. I passed by and forgot to tell you that. The IC ARIMA, remember there was an NA. This guy here would cause a problem when you're running, would stop your algorithm. This is why we're using a try, and then silent equals 0, and then the expression the ARIMA, and then the IC. This try allows us to have an error in one of our runs and for the algorithm to continue. Instead of showing a warning and stopping the whole thing, it just keeps on going. That's why we could continue running even though we found an error on 39 here. All right. I think I will do it again. Since I'm explaining at the end of the tutorial, I'll probably explain it again next time we use it. But for now, that's what we did today. We constructed an adequate set of ADF specifications. We carry out an ADF test, and then we constructed an adequate set of general ARIMA PDQ. Thank you so much for watching, and I'll see you next week.